Bearcats, this is 1.9 inverse functions. First of all, we're going to just define an inverse function. That is when if f and g are functions and they are inverses if f of g of x worked out is equal to x and g of f of x is equal to x. So in other words, the composition of f of g and the composition of g of f both equal x. Let's take a look at an example here and work that out together. So this is our f function and this is our g function. So first we're going to try f of g, which we're going to rewrite, remember, as f of g of x. And we're going to substitute in our g information, which is all of this, into our f function for the x. So we would have 7 times all of this chunk of information, x minus 4 over 7 plus 4. And then let's simplify this. Well, our 7's would cancel, and we would have x minus 4 plus 4. The 4's would cancel, and we would have x. Yay. So that tells me that that is a definition. We're proving that they are inverses. Now, let's go, that's part of the proof. Let's go the other way. So let's go g of f of x. This time we're going to take, I'm going to erase up here so you can see that better. So this time we're going to take our f information. Oops, I don't like that. Sorry. Our f information, and we're going to plug it in for the x in the g function. So we would have 7x plus 4 and then minus 4 all over 7. Well, the 4's would cancel. We would have 7x over 7, and the 7's would cancel, and we would once again have x. And they are both equal to x, so yes, we have, they are inverses of one another, so go Bearcats. Oops. Sorry. All right. Let's move on and to talk about graphing of inverses. If you need to pause, go ahead and then catch up with me in a minute. All right, next we're going to talk about graphing inverses. If they're inverses, they will reflect over the y equals x line, which is that linear parent graph, which is just that y equals x. And I'm going to go ahead and sketch that into our graph here. So it should look like it reflects over this line if they are inverses. So the first thing we're going to do here is we're going to actually sketch the graph, and then we're going to sketch the inverse. I'm going to show you how to do that. The first thing I'm going to do is I'm going to take this graph, and we want this graph only true for x values greater than or equal to 0. So I'm going to create a little t-table here. X and y. All right, I noticed in this graph they only want x values. This is a piecewise graph. X values greater than or equal to 0. So we want 0 and we want x values bigger. So 1, 2, 3. I'm going to plug these values into my equation and get an output. So 0 squared would be 0 plus 1 would be 1. 1 squared would be 1 plus 1 would be 2. 2 squared would be 4 plus 1 would be 5. 3 squared would be 9 plus 1 would be 10. That's probably going to be off my graph. So we'll probably just stick with these top 3 values. All right, so let's graph those. So we have 0, 0. We have 1, 2, and we have 2, 5. Okay, remember this is part of a quadratic, so our graph looks something like this. Something like this. All right, now to graph its inverse, we could go through and do a lot of things, but the quickest and easiest way, this is our f of x. To graph the inverse, which you denote with that little -1 up there, that represents an inverse function. Inverses simply mean we reverse our x and our y values. So this time, instead of 0, 1, we're going to graph 1, 0. Instead of 1, 2, we're going to graph 2, 1. And instead of 2, 5, we're going to graph 5, 2. Let's go ahead and put those on the graph. That should give us our inverse. So at 1, we're 0. At 2, we're 1. And at 5, we are 2. All right, so let's see if we graph that. Looks like that. And again, it looks like that would create our inverse function. Oh, I noticed something here that looked kind of funny. That's because this first point wasn't at 0, 0. It was at 1, 0. So my first point on the original graph should have been at 1, 0. I don't know if I can erase that without erasing a lot of things, so I don't think I'm going to try. But you understand the point. And you understand it looks like it's reflected over that XY line. All right, let's move on. If you need to stop and pause and write that down, that would be great. We're going to talk about two quick things here, and then we're going to actually go through a manipulation and steps to find an inverse algebraically. One-to-one function, the one-to-one function is where each value of the dependent variable, so each value of x, or all our x values, corresponds exactly to a value of the independent variable with y, which would mean it was a function. So that's for one-to-one functions. Not all inverses are functions, though. Horizontal line test. This can test not only if something is a function, but we're going to test if the inverse is a function. We're going to talk about horizontal versus vertical line test, which is the one you're familiar with. Okay, so let's take a look at two just quick sketches. Let's take a look at a quadratic. So if I have a quadratic, it passes the vertical line test. So if I have a vertical line going down like that, it passes through the vertical line test, so this would be a function. And we're denoting that because, I'm going to move this to the vertical line. Because of that vertical line, we can say this is a function. Now, what if I draw a horizontal line across my graph? When I draw that horizontal line, notice it crosses in two places. That means that my inverse would not be a function. Let's talk about what that looks like. So my inverse for this quadratic is going to look something like this. And you know the inverse then, if you're trying to determine if it's a function, would not pass the vertical line test either. So the horizontal line test sort of becomes the vertical line test of your inverse function. Let's take a look at one other example. So let's take a look at a square root graph. So we have a square root graph that's, let's say, just been shifted up one. So it looks something like this. All right, vertical line test. Okay, this would say it's a function. Happy face. All right, now, if I put a horizontal line test on this graph, this would also say it's a function. So the inverse would be a function. This also gets a happy face. Now let's take a look at what that would look like on a graph. I mean, if we graph the inverse. And if we graph this, it would look something like that. All right, let's take a look at our last problem of the day. We're going to find steps to find an inverse. Steps to find an inverse. Okay, first we're going to use the horizontal line test to see if the inverse is a function. Well, let's just talk about that. This is just a linear equation. So we know this is a linear equation with a y-intercept of -9 and a slope of -4. So our graph would be something like this. All right, and we know it would pass both the horizontal and the vertical line test. So the original is a function and its inverse would also be a function. To be able to write the inverse algebraically, we're going to replace f of x with y. So y equals -4x minus 9. And then we're going to interchange the roles of x and y. So we're going to switch out x and y. This is going to be x equals -4y minus 9. And then we're going to solve it for y. We're going to solve it for y. So we would add the 9 to this side, so we would have a -4y equals x plus 9, and then we would divide everything by -4. So y equals x plus 9 over -4, which would just make the whole fraction negative, or you could write it as -x over 4 minus 9 over 4. And I think that's probably the two ways I would write it. So that would be your graph. This would probably be easier to graph it if you were going to graph it from the equation. I would just take points on the line and reverse the order of the points. The last step here says verify the inverses by proving the domain of the original function is the range of the inverse. Well, we could do that by just testing a point if we wanted to. Let's say on this graph we know we have point 0, -9. 0, -9 is a point. Therefore, it should be that 9, 0 is a point. 9, 0 is a point. And if we graph this line, let's see if that's true. So we would want 0 to be, if we plug in 9 here, and that's a negative 9 plus 9, that would be 0 over 4, which would be 0. That would test true. And that would prove that our domain and our ranges have also changed places. All right, I think that's really it for tonight. We got 1.10 to do tomorrow night, and then next Wednesday will be your test. And I hope you have a great evening. Good night, Bearcats.